In Chapter 5, Section 1, we talk about systems of linear equations and two variables. A lot of the time, this is a review type section for a lot of students. So hopefully it will go pretty quickly and simply for you. When you have a system of linear equations, you're talking about any collection of two or more linear systems. Now we're going to focus on systems of two equations with two variables in this section. As we move in further into Chapter 5, we will talk about three variable systems and we'll talk about nonlinear systems as well. The solution set for any system is the set of all possible points that satisfy every equation in the system. So if it's a two variable system, it's the set of ordered pairs that satisfy every equation in the system. When we talk about a three variable system, it'll be the set of ordered triplets that satisfies every equation in the system. For a system of two equations and two variables, there we go. I get ahead of myself. These solutions come as ordered pairs. For a system with three variables, the solution would be an ordered triple. Now, when we get to that, you'll see that we typically use x, y, z as our variable for our third variable for our z-axis, our three-dimensional axis. Always go in alphabetical order, x, y, z. Okay, possible solution sets. There are three different ways your solutions can be graphed and your solutions can be discussed when we are doing linear systems of two variables. The first solution, where you have the first possibility, where you have one solution, is where your lines intersect. Now, because they are linear systems, this means that when I graph them, I'm going to be graphing two lines. If I have two lines on the same plane, well, there's only a couple of possibilities, right? So I have my two lines in the plane. Either those lines intersect or they don't. If they intersect, then they can intersect at any relationship. Possibly they might be perpendicular. That's an option. Either they intersect or they don't. Or this third possibility, I could actually have two equations that represent the same line, in which case the graph looks like a single line. So graphically, intersection, don't intersect, we call that parallel. Or you've really just got two equations representing one line, and you've got a single line because the graphs are on top of each other. All right, there's my little visual demonstration. Let's get them down on our notes. If my lines intersect, we call this a consistent system. And it's called consistent because it has a solution, which yields inconsistent will be when I don't have a solution. So down here, no solution, that's going to be an inconsistent system. Infinitely many solutions will be consistent because solutions. When I have one solution, I have intersecting lines. That consistent system is what we call independent. The lines are separate lines. They are independent of each other. Where I have no solution and I've got those parallel lines, my system is also independent because the graphs are independent of each other. Down here where I have infinitely many solutions, that's where I have a dependent system. That's where I have those lines on top of each other. Let's go ahead and graph some systems of equations. My one solution, the graph is going to look like, pretend that's a straight line for me. The graph is going to look something like this. I've got two lines on my graph, and those lines are going to intersect at a single point. Let's say that my point that they intersect at, it's in quadrant 1, so both of these values are going to be positive. Let's say it's 2, 4. That's the solution to that system. If I have no solutions, that's when I have the situation of parallel lines. They never intersect each other. So my graph is going to be two parallel lines. There's one line, here's a second line. I'm going to make them as visually parallel as possible. My solution is that there is no solution, the empty set. No solution. They are never going to intersect because they have the same slope. They're slanted to the same degree in the same direction. So we've got our one solution where they intersect, no solutions where they're parallel. Infinitely many solutions are going to be where I have two lines that are on top of each other. So let's do, there's my first line, and then here's my second line. Now, when I write the solution set for this, I say infinitely many solutions, but I need to represent it. And I represent it by giving at least one or the other of the two equations that are in the system. Let's say that this system is y equals negative x plus 1. I've got a negative slope. It intersects the y-axis at positive 1. And then my second equation might be 2y equals negative 2x plus 2. You can see that all I did was multiply the coefficient 2 times my first equation to get my second equation. So the graph is going to be the same line, same slope, same y-intercept. When I give my infinitely many solutions, I'm going to give that in set builder notation. I'm going to say every set of ordered pairs xy such that, and then I give either of these equations. It does not matter which one. I usually, whoops, that should be an equal sign. That's what happens when I talk while I write. I usually do whichever one is the quickest to write. Doesn't make any difference though. So all the ordered pairs xy such that they are a solution to this equation, they're a solution to the system, because this equation and the other equation are just multiples of each other. So these are our three possibilities for solution sets for linear systems. One solution where you have intersecting lines, no solution because you have parallel lines, or infinitely many solutions because it's really just one line on your graph. It's one equation and a multiple of that equation. The two possibilities where I have solutions are considered consistent systems. If there's no solution, that's an inconsistent system. In means not consistent. My two possibilities where the lines are individual separate lines are independent solutions. Where I really just have one graph, that is a dependent system because one equation depends on the other. This are the three possible solution sets for linear systems. Keep in mind, a line can only intersect another line in one location. If I had a nonlinear system, it's possible that I could have more than one intersection point. Okay, let's talk about whether or not an ordered pair is a solution to the system. Well, we gave our definition of a solution as the set of all possible points that satisfy every equation in the system. So how do we know if this is a solution? Well, we plug it in, and we have to plug it into both equations. So let's plug it into that first equation, 2x minus 3y equals negative 4. I'm checking the ordered pair 7, 6. So that would be 2 times 7 minus 3 times 6, and if that's a solution, that's going to give me negative 4. Well, 2 times 7 is 14, and then I have minus 18. And yes, 14 minus 18 is negative 4, so that works. Does that mean that this is a solution? We don't know yet. We have to check the other equation. So for it to be a solution, it has to work here and here. This one would be 2 times 7 plus 6 equals 4. And I can look at that and say, I got a problem, right? 2 times 7 is 14. 14 plus 6 is not 4. 14 plus 6 is 20. And 20 is not equal to 4. So that ordered pair is not a solution. Make sure when you do this type of problem that you answer the question. Check and see, and then make sure you answer the question. Okay, let's look at that next page. Okay, there are 3 different main introductory ways to solve a system of equations. We're going to find some other ways to solve systems later on, but right now we're going to work with these 3. The first way to solve a system of equations is graphically. You just graph the equations. You look at your graph, to see if they intersect or if they are parallel or if it's just one graph on top of the other. This is great, but generally this takes a lot of time. It generally takes more time to graph, especially if you're trying to find a specific solution. So you may be able to tell pretty quickly if they're going to intersect, but finding the actual coordinates of that intersection point can be a challenge because it's difficult to see the exact solution. What if the solution, the ordered pair, is not an integer solution? What if the solution is actually going to be 2.3 and negative 5.08? What if that's the solution to my system? Well, if I'm graphing to find that solution, I can see that if I do a pretty exact graph, my solution is about 2, negative 5, but I'm not going to know exactly what it is from the graph. Unless I'm not graphing by hand. If I'm graphing with a calculator, I could zoom in and identify that solution, but that's a lot of work. So generally, I use either the substitution or the addition method. So we've got some examples for substitution and addition method that we're going to go through. When I'm using the substitution method, first I narrow the equation down to one variable by substituting in an expression from the other equation. So for this first example, and let me kind of delineate where I have space. Okay, for this first example, I already have my second equation. I've got two equations, equation 1, equation 2. And equation 2 is already set equal to y. Y is the same thing as 3x. So I can take this expression, 3x, and substitute it in for y in the other equation, because it is equal to 3x. So I'm going to replace y in equation 1 with 3x. So that gives me x plus 3x, there's my substitution, is equal to 4. All right, x plus 3x is 4x. When I divide both sides by 4, I get that x is equal to 1. Now remember, I'm looking for the solution to the system, and that solution is an ordered pair. I found x. Now I need to plug that value for x into either equation and solve for y. It doesn't matter which one I pick, but it looks like it'll be simpler to solve equation 2. So I take this value for x and I plug it into equation 2. Y equals 3 times x, and I just discovered that x is 1. So y is equal to 3, which means my ordered pair, the solution, is 1, 3. That's my answer. I always put my answer as an ordered pair. Because I have a single solution, this system is consistent. It has a solution, and it's independent. They are two independent graphs, not the same line on top of each other, because they only intersect in one point. If I wanted to think about what these lines would look like, well, I'd have to see whether my slope would be positive or negative. This has a positive slope. That one, if I move that x over, would have a negative slope, and they're going to intersect at that point 1, 3 in the first quadrant. All right, let's do the second example. This one I'm going to have to do a little bit of work. I've got equation 1, equation 2. I see that this y does not have a coefficient, so I can rearrange equation 1 and solve it in terms of y. So I'm going to come over here and I'm going to rearrange my terms. If I move y over to the right, it becomes positive. So I have y over here. If I move 6 over to the left, it becomes negative. So when I rearrange this equation, I would have y equals 3x minus 6. Be careful as you're rearranging things that you get your positives and negatives correct. Okay, so y is the same thing as 3x minus 6, and that is going to be my substitution into the second equation for y. All right, so that makes equation 2 6x plus 5 times, make sure you use parentheses because I'm substituting in, is equal to negative 23. I have only one variable, so I can solve for that variable x. I need to distribute. And then I'm going to combine like terms on the left, so that gives me 21x. And I need to add 30 to both sides to move that constant over to the right. So 21x is equal to negative 23 plus 30 is 7. I finish solving by dividing by that coefficient on x. So I get that x is equal to 7 over 21, which simplifies to 1/3. That's my value for x. Now I need to finish solving for the solution, the ordered pair, so I need to get y. So I'm going to take this value for x and I'm going to plug it into either one of these two equations. It does not matter which one. Equation number 1 has lower coefficients, smaller coefficients, so I can keep my values smaller, so I'm going to choose that. 3 times x would be 3 times 1/3 minus y equals 6. Well, 3 times 1/3, that's the same thing as 3 over 1 times 1 over 3, which is just 1. So 1 minus y equals 6. If I subtract the 1, I get negative y equals 5. And then I divide by a negative because I have to finish solving for y. So y is equal to a negative 5. Make sure you don't stop there. All right, I found x, I found y. I need to write those as an ordered pair. That's my solution. And again, because I have a solution, this is a consistent system. And because it's a single solution, that means this system is independent. Okay, let's look at this one again. Remember, we want to work smarter, not harder, right? So we want to pick the variable that's going to be easiest to solve for. So I'm going to pick y again in equation 1 because it's the only variable that has a coefficient of 1. So I pull it out and I'm going to solve in terms of y. So I want my y to be positive. I'll move it to the right. That means I need to subtract the 9 and I get 3x minus 9 is equal to y. So y is the same thing as 3x minus 9. That's my substitution into equation 2. So I'm going to replace y in equation 2 with the expression 3x minus 9. So equation 2 becomes 2 times the quantity, 3x minus 9, minus 6x equals 7. Because I only have a single variable, I can solve for x here. Distribute your 2. Simplify by combining like terms. Well, 6x minus 6x, those are opposites. They add to 0. That leaves me with negative 18 equals 7. Or if I had moved that 18 over, I would have 0 equals 25. Either way, that's not true. So if I moved my 18 over, I ended up with 0 equals 25. If I left it, I have negative 18 equals 7. Either way, these are not true statements. When I get something here that is not true, as long as I haven't made a mistake, this tells me that I have no solution. I can give my solution as the empty set. So this system is inconsistent because there is no solution, which means they are two independent lines that they never cross. The graph, if I were to graph them, would be parallel lines. Okay, let's look at the next page. We have one more example of substitution method. This substitution method example gives us, well, it gives us fractions and it gives us, everything has a coefficient. So we've got to figure out something to get one of these equations solved for a variable that that has a coefficient of 1. I've got equation 1 and equation 2. Now I'm just going to tell you straight up that I would not solve this using substitution. I would start with addition. I'd clear out some fractions and go with addition. But we're told to use the substitution method, so we're going to do that. My second equation is already solved for y. It's just solved for 4y. So I can fix that by dividing everything by 4. That makes equation 2, y equals 3/4 x plus, and 12 divided by 4 is 3. So I've solved for y, and this expression is what I'm going to substitute in. Because I'm working with equation 2, that's the equation I solved for y, that means this expression is going to be substituted in for y into that first equation. Now it just dawned on me that every one of these we've substituted in for y, I think. That's just coincidence. That is not an on purpose thing. It just happened that way. So don't think that that's what you have to do. I could have solved for x and substituted in for x. The examples I gave you just worked best for y. Okay, so we are now working with equation 1, substituting this expression in for y. So I have 1/2 x minus 2/3 times 3/4 x plus, I'm going to go ahead and write that 3 is 3/1 because I know I'm working with fractions over here. It's going to make my life a little easier. So I need to do this distribution here. I have 1/2 x minus 2/3 times 3/4. Right here, those 3's are going to cancel and leave me with 2/4. Well, 2/4 x is just 1/2 x. And then I distribute here, 2/3 times 3, those 3's are going to cancel, and I'm left with minus 2, because that negative is what I'm distributing, is equal to minus 2, negative 2. Well, on the left, combine like terms, 1/2 x minus 1/2 x, those are opposites, they add to 0. So I'm left with negative 2 is equal to negative 2, and you know what, that is a true statement. That's true. Negative 2 is equal to negative 2. This is unlike what I got on the last one, where I got a statement that was not true. This is always true, which means I have found a dependent system. One equation is just a multiple of the other. I have a dependent system. Because it's dependent, that means I have an infinite number of solutions. It's consistent. Infinitely many solutions. So I have a consistent system that is dependent with infinitely many solutions. Anytime it has infinitely many solutions, that's dependent. And the way I write that solution set is to use fancy braces, set builder notation, all ordered pairs xy, such that, and then I plug in either equation. It really does not matter which one I write. I'm going to choose to write the second one this time. I could just as easily have written the first equation in there. Okay, so we've solved two systems that were consistent with a single solution, independent. We solved one system that was inconsistent, had no solutions, and we solved one system that was dependent, had infinitely many solutions. Now let's look at the addition method. This is our third method for solving linear systems of equations. Okay, to do the addition method, you're going to add the two equations together. And your goal is to add them together in such a way that you're adding an opposite so that one of your variables adds to 0. To make that happen, you may need to multiply one or both of the equations by some coefficient so that you create those opposites that will add to 0. When you use the addition method to and multiply by a coefficient, you're creating what we call an equivalent system. You are creating one equation or two equations that are equivalent to what you started with. For this first example, I don't have to do any multiplying because when I look at this, those are already opposites. My y's are going to add to 0. So I just do my addition. I just add those two equations together. When I'm adding, I always have to add like terms. 3x and 2x is 5x. That negative y and positive y adds to 0, and that's equal to 10. Finish solving for x by dividing out that coefficient, and I get x is equal to 2. Now I have to go back and plug that into either one of my equations to solve for y. Does not matter which equation I pick. Let's go ahead and plug into equation number 1. That would be 3 times 2, because we said x is 2, minus y equals 9. So that's 6 minus y is 9. Negative y is equal to 3. And then I have to finish solving for y. I can't stop at negative y. So I get that y is equal to negative 3. My ordered pair, my solution, is 2, negative 3. Make sure you write it as an ordered pair. Have a single solution, so this is a consistent, independent system. All right, let's take a look at this next one. Again, I have equation 1 and equation 2. I want to create a system where I can add one of my two variables, either x's or y's, and they add to 0. So I need opposites. My y's would be a little tricky because 5 and 3 don't have anything in common. But here I have 4 and 2. 2 times 2 is 4. I need one of them to be negative. So let's go ahead and just multiply this second equation times a negative 2. When I do that, I'm not changing the first equation. I'm just rewriting it. 4x plus 5y equals 3. I don't need to change anything there. But for the second equation, I am multiplying everything in this second equation times negative 2. So negative 2 times 2x is a negative 4x. There's my opposites that will add to 0. Negative 2 times negative 3y is a positive 6y. And negative 2 times 7 is a negative 14. Now I add those equations together. I created an equivalent system by using a multiple of the second equation. 4 and negative 4 add to 0, so I end up with just 11y is equal to a negative 11. When I divide by that coefficient on y, I get that y is equal to negative 1. I need to plug that value for y into either one of my equations. We used the first equation here. Let's use the second equation for this problem. 2 times x minus 3 times y, substitute in my value for y, is equal to 7. So I have 2x plus 3 is 7. I move that 3 over by doing the opposite or the inverse operation. Then I move the 2 over by doing the inverse operation, and I get that x is 2. So I have my ordered pair. XY ordered pair is going to be 2, negative 1. Again, I have a single solution, so that tells me if I graph it, they're going to intersect at that location, 2, negative 1, in quadrant 4, and I have a consistent, independent system. Now the next page contains 3 more examples for our addition method. We're not going to do that right now together. As I've said before, if you are in a fully online class, work on these examples, see what you get, and then you can come check with me later to see if you're correct. You know what? I'm going to do you one better. I'm going to give you the answers so that if you are working on your own, you'll know if you were right. If you have Meet with Me in BBCU, we'll talk about it then. So this one is going to be a dependent system, and you should know what that means. Okay, let's look at the next page. We are going to talk about an application, and then we're going to talk about break-even analysis. Where do we see systems of equations show up? Well, a lot in finance or when you are calculating mixtures and things like that. Let's work through this application problem together. Thanks to a gift from your step-uncle, you invested $100,000. Oh, I want that step-uncle. You invested $100,000 in 2 mutual funds, so 2 investment accounts at the beginning of 2020. Oh, wow. Yeah, this was a different 2020 than we're actually living in. I wrote this in 2019. By the end of that year, Oh, well, maybe not. By the end of that year, both funds had lost value. I was thinking it was a problem where we gained. By the end of that year, both funds of investment lost value. Fidelity Balanced was one of the funds, and it had lost 32% of your investment. Fidelity Value had lost half, 50% of your investment. The losses totaled $42,800. How much money was invested in each fund? Well, we're going to treat this by writing a system of equations. We have information about percentages lost, and we have information about total values, total dollar amounts. So we're going to write a totals equation, and we're going to write a percentage equation to get our system. Let's call Fidelity Balanced B, Fidelity Value V. I invested some money in Fidelity Balanced, some money in the value account, and the total of my investment was $100,000. That's how much I had to invest. Then I have my losses. Balanced lost 32%. So I'm going to go ahead and change that to a decimal. I lost 32% or 0.32 of the money invested in the B fund. I lost 50% or 0.5 of how much was invested in that value fund. And the total amount lost was $42,800. So now I have a system of two linear equations and two variables. We're going to solve that system, and we can solve it however we want to. You can solve it using addition, or you can solve it using substitution. We're going to go ahead and go back and solve this using substitution, because if I look at this first equation, I can solve it simply in terms of B or V. Let's go ahead and solve for B. If I solve for B, that means I'm subtracting the V from the other side, which gives me 100,000 minus V. That's my substitution for B into my second equation. So I'm going to substitute that in for B in my second equation. That gives me 0.32 times 100,000 minus V plus 0.5 V equals 42,800. Let's distribute here. We get 32,000 minus 0.32 V plus 0.5 V is equal to 42,800. Okay, next step is going to be to combine like terms on the left, and I can move this 32,000 over to the right. 0.32, a negative 0.32, and a positive 0.5 gives me 0.18 V, equal to 42,800 minus 32 gives me 10,800. And then I divide by that coefficient. This is calculator math. Make sure you plug it in. You get out a nice number. You get out that V, the amount invested in Fidelity Value account, comes out to be $60,000. Now notice that I didn't just pick X and Y as my variables. I tied my variable names to the problem so that when I got to the end, I knew what my answer meant. I didn't have to guess. The value account, Fidelity Value, had an investment of $60,000. Well, what does that mean? How much was in the balance, Fidelity Balanced account? Well, it was the rest of the money. I can either plug this in and solve, or no, I had $100,000. If $60,000 went here, that means the other $40,000 went there. Go back and reread your problem. Make sure we've answered the question, and we have. Okay. Now we're going to talk about break-even analysis. Break-even analysis is another place in business where you see systems of equations being used. Break-even analysis. When you're running a business, there are certain basic calculations you need to take into account. Things like fixed costs versus cost per item, the difference between profit and revenue, and where that break-even point falls. My break-even point is when I have brought in as much money as I have spent. So I've got $0 in the bank, but I'm not in debt. Now, this break-even analysis idea is why I never let my daughters do a lemonade stand growing up. They always wanted to do a lemonade stand because they wanted to make money. What they didn't realize was that by the time they paid for what they bought, for the lemonade and the cups and the brownie mixes, because they always wanted to sell brownies with the lemonade, they weren't going to make any money because you had cost that goes in at the start. Now, when you have cost, this cost is going to include your setup and your materials and labor. So setup is what we have that's kind of that fixed cost. Setup for a lemonade stand would be the cost of the table and chairs, the sign, things that you have to do that once you do them, it's done. You don't have to keep putting money back into that for the most part. Materials and labor, however, that goes into your cost per item. Materials and labor would be free for the lemonade stand, but the materials are going to be the lemonade mix, the cups, the napkins, the brownie mix. Those are materials and labor costs. Those come out to cost per item. So you can kind of figure out how much each of these costs per item, but then you've also got to take into account that setup cost. Revenue. Our revenue is our total income. So if you're running the lemonade stand, the revenue is the amount in your jar at the end of the day. Revenue is not the same thing as profit. Profit is that revenue money that you brought in minus the cost that you already paid out. So when we start talking about these in terms of functions, we're going to have a cost function. We're going to have a revenue function. And our profit function, P of X, is going to be equal to that revenue function minus the costs. My break-even point occurs when my cost, the money I spent, is equal to my revenue, the money I bring in. So in terms of functions, my break-even point occurs where the cost function is equal to the revenue function. Okay, let's work an example. You and your best friend decide you're going to start a company making running shoes. It's going to take you $300,000 to set up the factory. And then there's labor and materials costs of $30 per pair of shoes. So you got to get your setup going, and that's going to take an investment of $300,000. Then as you're producing shoes, the cost per pair is $30 per pair. That's your labor costs, that's your materials that go into the shoes, maybe electricity. You decide you're going to sell the shoes for $80 a pair because you want to make some money, right? You can't sell them for $30 because then you're in debt this $300 and you're not making anything. So you've got to make back your money, and you've got to eventually want to turn a profit. So let's look at our cost function first. My cost function is, well, I had to get a loan for that $300,000 to set up the factory. And then as I make shoes, it's going to cost me $30 per pair of shoes, where X is the pairs of shoes. Revenue function. Well, revenue is the amount of money you're bringing in. That's based on how much you charge. We decided we're going to charge $80 per pair of shoes. So every pair of shoes I sell, I get $80 for it. If I sell one pair of shoes, I made $80. If I sell 100 pairs of shoes, it's 80 times 100. Profit. My profit function is my revenues minus my cost. Well, that revenue we said is 80x. And we need to subtract from that my cost function. So that $300,000 setup plus $30 per pair of shoes. That gets me to 80x minus 300,000 minus 30x. And when I combine those like terms, I get a profit function over here. It took me a little space. 80 minus 30 is 50x minus $300,000 because I've got to take into account that factory setup. So I don't get to profits until I bring in that $300,000. What's my break-even point? When am I out of debt, but I got $0 in the bank? So I still can't go to Starbucks and get a chai latte, but I don't owe anybody anything either. Well, that happens when cost is even equal to revenue. My cost was $300,000 plus 30x. My revenue is 80x. So when are those equal? Well, let's solve this equation. We're going to subtract that 30x. So we've got $300,000 and we've got a profit of an income per pair of shoes, 50x. So how many pairs of shoes do we have to sell to have $0? Well, if I divide 300,000 by 50, I get a value for 6,000. X represents how many pairs of shoes. So when I have made and sold 6,000 pairs of shoes, I've broken even. I have $0. But how much money have I brought in? How much money have I spent? Well, to figure that out, I need to solve either my cost or revenue function. It doesn't matter, either one, but the revenue function is simpler. So if I do R of X as R of 6,000, because that's the number of pairs of shoes where I've broken even, I've got 80 times 6,000, which means, because that's $80, right? That's $480,000. That's my break-even point. If I write that as an ordered pair, that's 6,000 and then 480,000 on a graph. That's my break-even point. When I have made and sold 6,000 pairs of shoes, I have spent and brought in $480,000. Is that my bank account? No. That's where I've broken even. That's where I have $0, but I'm no longer in debt. All right, there's one more application page included with your guided notes. I'm not going to go through that as part of the video. So that's all for today.